So let's start from the first speaker, Shinji Mukohyama, and he will talk about minimalism in modified gravity.
Okay, thank you very much. Okay, I'd like to thank organizers for a kind invitation. And today I'd like to talk about minimalism in modified gravity. By the way, can you see my pointer?
Yes, we can see it.
Yeah, thank you. And this is based on my collaborations with these people. And so let me start. Okay, so introduction, the motivation for modified gravity. Okay, so probably I don't need to do this, but just in case. Okay, so the first motivation comes from mysteries in the universe, such as dark energy, dark matter, inflation, Big Bang singularity, and cosmic magnetic field, and so on. So if we can replace some of them by modification of gravity, that would be great. Okay, and the second motivation comes from quantum gravity, and so if modification of gravity can help unifying quantum mechanics and gravity, that would be great. So for example, superstring theory is, I think, from my point of view, is modified gravity, and Hoja-Lipschitz gravity, and so on. This kind of modification of gravity at short distance. Okay? And even if the gravity, I mean, so probably at least at short distance we need to modify gravity, but there is a possibility that at long distance, GR may be the correct description of gravity. Even in that case, if we want to prove it by experiments or observation, it's I think one of the best ways to predict the possible deviation from GR and then constrain those deviation by experiments or observation. So in this sense, in order to understand the GR itself, I think modification of gravity is very useful. And after all, one of the best ways to understand something, maybe just break it and then reconstruct it, I think. Okay. So you may have other motivations, but at least there are three motivations. Okay. And from the point of view of the last motivation, I think we do better understand GR. Of course, I mean, before modifying gravity. And after modifying gravity, maybe we understand GR better, but from the beginning, I think we should understand better GR. Okay, so let me remind you how we can count the number of degree freedom in general relativity. Okay, so we start from 10 metric components, and then we go to the phase space because Hamiltonian formulation is very useful. Okay, so we go to the phase space, which means we multiply 10 by 2, so we are in the 20-dimensional phase space at each point. And then in order to do that, I think I mean, we need to consider time and space in a different way, so that the so-called ADM decomposition is useful. Okay, so the metric is written in this way by lapse and shift and the 3D metric. Okay, and then plugging this to the Einstein-Hilbert action, we get this expression. Here, Kij is extrinsic curvature defined in this way. So this includes the time derivative of 3D metric here, okay, this one, but that doesn't include the derivative of lapse or shift. So the Einstein-Hilbert action does not contain time derivative of n on ni. So the corresponding conjugate momenta are zero, identically. So they are algebraic equation in the phase space. Therefore, they are called the constraints. Okay, constraint can remove the number of degree freedom in the phase space, and especially these 1 plus 3 in total 4 constraints kind of the so-called first class constraint, because all constraints are independent of lapse and shift. So that if we compute the Poisson bracket between this guy, for example, and other one, then they all of them vanish. And let me explain what first class is and what second class is. Basically, first class is better than second class, as always. And second class constraint can reduce one phase space dimension. Okay. On the other hand, first class constraint can reduce two phase space dimensions. And in this sense, first class constraint is better. And also, the first class constraint is associated with symmetry. So that they generate symmetry. Okay. And because 2 is 1 plus 1, so the one first class constraint is equivalent to a pair of second class constraints. Okay. For example, if we start from first class constraint, we can add gauge fixing condition, which can be considered as a constraint by itself. So then the first class constraint is downgraded to second class. So we end up with the pair of second class constraint. That is equivalent to original first class constraints. Okay. So now here we have 4 first class constraints, but also, as I said here, the first class constraint is associated with symmetry, and they are not associated with the 4D diffeo. But GR has a 4D diffeo, so that we have additional four first class constraints. They are momentum constraints and Hamiltonian constraints that we know. Okay, and so in total we have 4 plus 4 first class constraints. Therefore, starting from 20-dimensional phase space, we end up with 4-dimensional physical phase space. Okay, because each of them reduce 2 phase space dimensions. Okay, so this corresponds to 2 local physical degree freedom, okay, corresponding to the plus and cross gravitational polarizations. Okay, but this is fully nonlinear. Okay, and this means that when we modify gravity, and also we know that in our universe there are gravitational waves observed. So the minimal number of degree freedom in modified gravity should be 2. Okay, 2 or larger. Okay, so therefore, so question here is, can we saturate this number? Okay, can we find the modified gravity with a 2 degree freedom? That is a question that I would like to ask in this talk. Okay. And so those theories that satisfies this, saturate this number is called minimally modified gravity. Okay. And so the question is this one. So is general relativity unique? So if the answer to this question is yes, then the answer to this question is no. Okay. However, so usually people, we tend to say yes to this question and no to the previous question because of the following reason. For example, Lovelock theorem says yes if we assume these 4 assumptions, 4 dimensions and diffeo invariance and metric only, and up to second order equation motion of this form. Okay, and also the effective field theory or derivative expansion tend to say yes also if we assume the following 3. Okay, 4 dimensions and diffeo invariance and metric only. Okay, under these assumptions, we can construct action of the theory from metric and its derivatives. And as we know, if we don't include the derivatives, then the only scalar made of metric is just a constant, which corresponds to cosmological constant. With first derivative, there is no scalar, additional scalar. With 2 derivatives, we can find a rich scalar. Then if we truncate at the second derivative, then we end up with GR. Okay, this is Einstein-Heat reduction. So in this way, effective field theory also tend to say yes to this question and no to the previous question. However, in these 2 arguments, we assume 4D diffeo. This assumption 2 and this assumption 2 are 4D diffeo. On the other hand, the cosmological background breaks 4D diffeo while keeping 3D diffeo. So maybe this assumption may be too strong. Okay, so question that I want to ask whether we can find a theory with 2 degree freedom with 3D diffeo, but with broken 4D diffeo. Okay, so this is a question. But typically, if we try to find such theory, then we tend to end up with 3 local physical degree freedom. For example, scalar-tensor theory, EFT of inflation, EFT of dark energy, or Hodge-Fixed gravity. Okay, let me explain this by simple example. Okay, so this is a simple scalar-tensor theory, okay, described by this covariant action. So this is a 4D curvature multiplied by some function of scalar field. Okay, and this includes a kinetic term and the potential of the scalar field. X is a usual kinetic term, but this can be nonlinear or linear. Okay, and then let's try to remove phi from the description by adopting the ADM decomposition that I described before and the so-called unitary gauge. Okay, so phi is said to be time. Okay, this is good as far as the derivative of phi is time-like. Okay, whenever derivative of phi is time-like, we can take this gauge and this is okay. Okay, then plug in this and this to here, we get this kind of action. Because of this gauge, scalar field kind of disappeared from the description. So that everything is written in terms of the metric in the 3+1 decomposition. Here, this Kij is again extrinsic curvature, including the time derivative of 3D metric, and this is 3D curvature, and so on. Okay. So, but although this is described by only the metric, we know that the number of degree freedom is 3, because this is equivalent to this line. Okay. Metric and the scale, so that we have 3 degree freedom. Okay. So real question here is this one: is GR unique when we assume these 4 assumptions, 4 dimensions and 3D diffeo instead of 4D diffeo, and the metric only, and the 2 local physical degree freedom? That corresponds to there are 2 polarizations of transverse stressless gravitational waves. This is a question that I want to ask. Okay. And the answer turned out to be no, which means the previous question, answer to the previous question is yes. And so the theory that satisfy these 4 conditions, which is not GR, is called the minimally modified gravity. I hope this is clear enough. And here I'd like to explain some examples of type 1 and type 2 minimally modified gravity. For this purpose, I think I need to explain what type 1 is and type 2 is. Okay. So this classification was introduced in this paper. And but this classification applies to any modified gravity. So let me explain this. Very simple one. So let's consider scalar-tensor theory of this type. So the 4D curvature is multiplied by a function of scalar field. And this dot includes the kinetic term and the potential for scalar field. And in this description, the so-called Jordan frame or matter frame, the matter action is very simple. Okay, matter minimally coupled to this metric. Okay, that's why this is sometimes called matter frame. Okay, but we can simplify gravity action by performing the conformal transformation in this way. This omega is the same as this omega. Then this omega is removed, and we end up with something like Einstein-Hewitt action. So this coefficient is just a constant. Okay. So do we call this GR? Actually, no. This is indeed modified gravity because matter action is a bit more complicated. Okay. So matter couples to this combination, so that when matter is excited, not only the metric in this frame, but also scalar field is excited, and they propagate according to this action. And then what we observe is this combination. In this way, gravity is modified. Let's call this type of modified gravity type 1. Okay. In this case, gravity is modified because of non-trivial matter coupling. Okay. There are, however, more general scalar tensor theories where there is no Einstein frame. Let's call them type 2. Okay. Let me repeat. Type 1, there exists an Einstein frame, therefore can be recast as GR plus extra degree freedom plus matter. Okay, which couples non-trivially by change of variables. This is type 1. Type 2, no Einstein frame, therefore cannot be recast as GR plus extra degree freedom plus matter by change of variables. Okay, so this classification is completely general, and anything that is not type 1 is type 2. Okay, so let me explain some examples. Type 1, minimally modified gravity. By definition, the number of degree freedom is 2, and there exists an Einstein frame. Therefore, this kind of theory, any type 1 minimally modified gravity can be recast as GR plus matter, which couples non-trivially by change of variables. In other words, we can start from GR and perform change of variables to get all type 1 minimally modified gravity. This is completely general. Okay? And as far as I know, the most general change of variables is canonical transformation. So that we can just perform canonical transformation to GR. This is completely systematic and general. Okay? However, matter coupling is a bit non-trivial. Okay? If we just introduce matter coupling after canonical transformation, this is inconsistent because the matter field supposed to have some 4D diffeo, for example, if we assume 4D diffeo. And however, on the other hand, gravity part by itself also has a 4D diffeo. hidden. I mean, so because we started from GR and perform change of variables, so it is still GR before adding matter. So it has a GR, it has a diffeol, but it's kind of non-trivial. And the diffeol in the matter action and the diffeol in the gravity action are different if we try to couple matter after canonical transmission. So if we put them together, they are not consistent. In other words, symmetry is broken. Therefore, the first class constraint is downgraded to second class. Okay, no more associated with symmetry. Therefore, and as I said, second class remove only one, first class two, so that we end up with extra degree freedom in phase space. That is inconsistent. However, it's easy to fix this. We can just gauge fix after canonical transformation before adding matter. In this case, the first class constraint splits into pair of second class constraints, and they remain after adding matter. Therefore, this is completely consistent. We can add matter after canonical transformation and gauge fixing. Then the pair of second class constraints remain. This is consistent. This is completely general and systematic way of constructing all type 1 minimally modified gravity. And there are many examples, and I don't have time to explain all of them, but one of them is this one, okay, what we call f of h. And because, I mean, we call this f of h because constraint in this theory is an arbitrary function f of constraint in GR. H is a constraint in GR, Hamilton constraint in GR. So in the absence of matter, by setting f equals 0, h is said to be root of this function. So this is equivalent to GR in the absence of matter, but with the presence of cosmological constant. Cosmological constant is given by basically root of f. Okay, but after gauge fixing and adding matter, this is not equivalent to GR. Indeed, by choosing some form of function f, we can fit the Planck data better than lambda CDM. Okay, so this is physical. Okay, physical difference from GR. Okay, so this is one example, and this indicates that we may have some transition in haploid expansion rate at around this within this model. Okay, but I'll skip the details of this model. Okay, I just wanted to say that by just doing canonical transformation and fixing gauge and adding matter, we have different theory. So this is type 1 minimally modified gravity. Okay, so let me explain type 2 now. Okay, type 2 minimally modified gravity has two local physical degree freedom by definition, and there is no Einstein frame. Therefore, cannot be recast as GR plus matter by any change of variables, any. Okay, so is there such a theory? Indeed, yes. One example is minimal theory of massive gravity that I just developed with my colleague Antonio Di Frecce, and probably I will explain this later, as far as if I have time. And but now I want to explain another example that was developed in this paper. Okay, and we call this VCDM because we replace lambda in the lambda CDM by function V of some auxiliary field phi. Phi looks like a scalar field, but indeed it is scalar, but it is not dynamical. So there is no extra degree freedom. Okay, so construction is very simple and similar to type 1. Okay, we started with the GR in Hamiltonian formulation, of course with 3% decomposition, and perform canonical transformation to a new frame. Okay, and if we stay there, that is type 1. But we just add cosmological constant and gauge fix and come back to the original frame. Okay, perform inverse canonical transformation back to the original frame. Then go back to the action or Lagrangian by Legendre transformation, then add matter. So in a sense, we make a trip, then pick up the cosmological constant and come back. Okay, in the case of type 1, we make a travel, we stay there. Okay, we don't come back. But in this case, we come back to the original frame. This is how we constructed this theory. And action is given by this. And later, actually, we found that this is equivalent to what is called Cascaton. And also, in addition, we proved that there is no Einstein frame. It was not, I mean, we were kind of lucky. So because it is not easy to prove that there is nothing, there is no Einstein frame, because even if we try to find Einstein frame and fail, it does not provide a proof of absence of Einstein frame, but somehow we proved. Okay, so I'll explain it later. Okay, anyway, so this theory has one free function, and this free function can be reconstructed from Friedman-Robertson-Walker background. Any background can be implemented. Okay, bouncing or kind of equation state parameter W less than -1 or whatever. Okay, we can reconstruct the V. Okay, and speed of gravitational wave is 1, and there are no extra degree freedom. So it's very, very easy to satisfy constraints. Okay, and what is nice is about this theory is that we can reduce H notation by using this property. Okay, by giving some potential, we can find background evolution that can reduce H notation. Also, recently we extended this theory, so namely the beyond the Cascadon, to address both H notation and S tension. Maybe I have time to explain this. I hope. Maybe not. I don't know. Okay. Anyway, so this is how we prove that this theory doesn't have Einstein frame. Okay. So in order to do that, it was very useful to refine the classification. Okay. We already have type 1 and type 2. Type 1 have Einstein frame, type 2 doesn't. And on top of this classification, we introduced a subclass A and B. A has a standard dispersion relation for gravitational waves. Subclass B doesn't. So in the case of type 1A, the relation between the Einstein frame and the matter frame are just proportional to each other. So the canonical transformation is conformal type. And type 1B, in this case, relation is not conformal type. So the speed of gravitational waves changes, okay, compared to the speed of light. Okay. On the other hand, type 2B, this is standard dispersion ratio is modified, but we want to have 1 here so that we can have mass, or we can have higher order terms in the dispersion relation, K to 4 or K to 6 and so on. Okay, so these two examples have a modified dispersion relation for gravitational waves. Okay, and we wanted to show that this VCDM or Cascadon is here. Okay, so let me explain how we prove. Okay, so first we analyzed the gravitational waves in these theories and found that dispersion relation is the same as GR. So therefore, this theory should be either type 1A or type 2A. Okay, and then we constructed all type 1A minimally modified gravity by starting from GR and performing conformal type canonical transformation. So we knew all type 1A. Then analyze the vacuum Bianchi 1 universes in this theory, Cascadon or VCDM, and general type 1A minimally modified gravity. Then we found that dynamics is different. Therefore, this theory is not type 1A. So combining 1 and 3, we show that this theory is type 2A. Therefore, there is no Einstein frame. So we now populate here. We now have all types of minimally modified gravity. Okay. And recently, we, as I briefly mentioned, we recently so extended this VCDM or Cascadon to realize weaker gravity for dark matter. Okay, this may be useful for SA tension. So the construction is very similar to VCDM, and only difference is we introduce dark matter action in the new frame. We make a trip, and we pick up not only the dark cosmological constant, but also dark matter there, and come back. This is how we constructed. Okay, and action is this part gravity action is the same, but while standard model couples to the standard metric, the dark matter couples to this different metric. Okay, so by choosing these functions properly, we can reconstruct any h of z, Hubble expansion rate as a function of time or redshift, and also the effective gravitational constant for dark matter. Okay, we can reconstruct them because we have two free functions. Okay, and on the other hand, gravitational constant for standard model is the same as GR. Therefore, it's very easy to satisfy the constraints. Okay, and also speed of gravitational wave is 1. Okay? And this may reduce H0 tension and isolate tension. We are working on this now. Okay, now but after explaining some example of type 1 and type 2 in the remaining time, I'd like to explain some massive gravity examples. Okay, how many minutes do I still have?
About 5 minutes.
Okay, so let me try to finish in 5 minutes. Okay. So maybe not everyone is familiar with massive gravity. So let me explain massive gravity in a nutshell. Okay, very brief way. Okay, so original motivation came from this simple question in the classical field theory: can graviton have mass? Spin to field can have mass or not? Okay, the answer turned out to be time dependent. Therefore, I put here seesaw or balance. Okay. So this changes, that answer changes. First answer was yes, by definition, because otherwise history didn't start. And the answer was given by Fierce and Parry. They found the unique linear theory in 1939. And some years later, BDBZ came up and they showed that the massless limit of this theory does not agree with massless theory, namely GR. Okay. And the difference is order 1. And if this is correct, both mathematically and physically, then the massive gravity would be excluded by experiments, however small graviton mass is. Okay. And then 2 years later, Weinstein came up, fortunately, and the answer changed to yes. And he showed that when we send the graviton mass to small, then actually 0, then the nonlinearity becomes important, and linear theory completely breaks down. And because of nonlinearity, massless limit agrees with GR. Okay, this is this is what he showed. So in a sense, nonlinearity saved the massive gravity. However, in the same year, the same nonlinearity caused a problem. So the Boroya-Deza showed that because of nonlinearity, extra degree freedom appears. In a sense, fine tuning invoked by Fierce-Parry was detuned at the nonlinear level. Okay. Since then, almost for 40 years, people believe that there's no way to give a mass to graviton. Fortunately, almost after 40 years, Durham-Gabatti and Torrey found a way out. They found the first example of nonlinear massive gravity without BD ghost. Okay, so this was good, and therefore the answer to this question may be yes. Okay, and it's time to ask the second question: can we have acceleration without dark energy? But the first answer was bad, and the people found that there's no flat Friedman-Robertson Lemaitre-Robertson-Walker universe in this theory. Okay, so a consistent theory was found, but no viable cosmology. That was the time when I started to think about the theory. So maybe bad timing or good timing, depending on the outcome. Okay. And then I found that, fortunately, we found that open universe may be okay. So we found the open universe with self-acceleration. And also, by slightly changing the theory, we found that also closed and flat universe can be accommodated. So we found some good results. But as you can expect from the fact that I still have seesaw, we had a bad result. Okay, after that, we found that this theory has a nonlinear instability around this nice solution. Okay, at the linear level, some degree of freedom are hidden, and at the nonlinear level, they show up and they become ghosts. And this ghost is within 5 degree of freedom, so this is not BD ghost. And this is not Higuchi ghost because this is at the nonlinear level. So we found a new phenomena. In that sense, we are happy, but at the same time, we were sad because we killed our own solution. Okay. Naturally, we try to find a way out. One possibility is to find a new class of solutions, which we call anisotropic Friedman. Probably I don't have time to explain this, but we need to break anisotropy or homogeneity to find a new class of solution. And another possibility is to modify DRGT. Okay. One possibility is this minimal theory of massive gravity. So this is how minimalism may be useful. We found a theory of massive gravity with 2 physical degree freedom only. and they correspond to two massive gravitational waves, and there are no scalar or vector modes. So there are no instability. And what is nice about this is that we can find exactly the same Friedman background as in DRGT, so that we can find the accelerated universe without dark energy. Just graviton mass can accelerate the universe. Okay. And there are no BD ghost, no Higgs ghost, no nonlinear ghost, and so absolutely stable. And there are no, so that also the positivity bound does not apply. So this is also nice. And so this theory has same Friedman background, but there are two branches. One branch is a so-called self-accelerating branch, so we can accelerate the universe. But scalar and the scalar and vector perturbation behave exactly the same as lambda CDM. So the prediction is the same as lambda CDM. This is a red line corresponds to lambda CDM, which is self-accelerating branch of MTBG. So this is safe, but a bit boring. And so we try to consider another branch, which we call the normal branch. In this case, behavior of scalar and vector perturbation are a bit different. Vector is the same, but the scalar perturbation is different. And we try to fit the RSD data. And we found that the fit is a bit better. And we found two minima of the chi-square, and this one and this one. Each of them fit a bit better than lambda CDM. So minimalism may be useful in this sense. And also, if we try to apply this idea to the early universe, this is also interesting, and we can find blue-tilted and amplified primordial gravitational waves from minimal theory of mass gravity. Okay, so for this purpose, we have to slightly extend this theory by changing the constants parameters in this theory to a function of an extrascalar field, so that the mass of graviton changes from large value in the early universe to the small value at the late time. At late time, we want to satisfy the constraint from LIGO, and on the other hand, we want to have large value in the early universe to be for graviton mass to be effective. Okay, so in this case, we imagine that the graviton mass changes from large value to small value at some point between reheating and BBN. Okay, and therefore, during the time between reheating and this time, the graviton behaves like massive particles. So the energy density scales like A to -3 instead of A to -4 as in GR. Therefore, decay is slower than GR. So in this sense, the because of the transfer function, the amplitude is larger than GR for the same primordial amplitude. Okay, and also because of the graviton mass, we expect to have a blue-tilted spectrum. Namely, the red part is suppressed, but the blue part is not. Okay, so for example, after imposing a constraint from CMB, we can still have this kind of, for example, this kind of shape, or this kind of shape, so that we can detect the gravitational waves by many detectors. Okay, so in this sense, again, the minimalism may be useful. Without minimally modified gravity, it's not easy because of the huge bound and so on. Okay, so the minimal theory mass gravity may be way out, and also you may wonder whether we can promote the so-called physical metric to the dynamical one to find the minimal version of bigravity. Actually, we did very recently. Actually, after this paper, for a long time we tried to find this theory, and we couldn't. But somehow we recently found, with the help of two young people, and Francois and Michele. Fortunately, we found a way out. And this theory has only 4 physical degree freedom, corresponding to massless and massive gravitational waves. And this allows for exactly the same Friedman-Robertson, Lemaitre-Robertson-Walker background as in Hassan-Rosen bigravity. So we can have a self-acceleration without instability. There's no instability, like no BD ghost, no Higgs ghost, no strong coupling at all. So completely stable. And this is a way how to derive this, but probably I don't have time. So let me explain this. So this is a very fast example of completely stable and cosmologically viable theory of nonlinear bigravity. And this can provide us a testing ground for gravitational phenomena such as graviton oscillation and also maybe the dark matter, I mean, graviton, massive graviton as dark matter, that can be proved by, for example, gravitational waves. Okay, so this may be another way out. Okay, so let me summarize. So the minimal number of degree of freedom in modified gravity is 2, and this can be saturated, leading to minimally modified gravity. Type 1 minimally modified gravity has Einstein frame, type 2 doesn't. And I explained some example of type 1 minimally modified gravity, but systematically we can generate all type 1 minimally modified gravity starting from GR, performing canonical transformation and gauge fixing and adding matter, that's all. But we have rich phenomenology, such as effective equation state and G effective and so on. And f of h theory can fit Planck data better than lambda sigma. So this is completely actually physical difference from GR. And also I explained some example of type 2 minimally modified gravity. One example in minimally theory of massive gravity. And another example is VCDM and Cascadon. And also the extension of this to address the H0 tension and S tension. Probably I'll skip the summary of massive gravity part. Thank you very much.
Thank you very much, Shinji. So we have 5 minutes for questions. Please raise your hand. Then ask a question.
Andre is raising hand.
Please, Andrei.
Okay, thank you. Well, Shinji, thank you very much for a very interesting talk. Really exciting. And maybe you can bring us back to one of the slides where you considered your Kuskouton related model. Can you do this?
Sure. This one?
Basically, my question is the following, whether I correctly understand what you suggest. Well, the model is very peculiar in the following sense, that this is a model which has a kind of a very non-trivial square root structure of this X kinetic.
If we want to restore the 4D diffeo, we can introduce a kind of scalar field as a Stuckberg field, and then yes, it has square root. Yes.
How to see actually this non-trivial structure in this Lagrangian, because this Lagrangian
yes, right. It's not trivial. Yes, actually, yeah. But actually, we can start from Cascadon, and then Cascadon has a scalar field, but we can choose the unitary gauge and to remove scalar field. And after eliminating some, I forgot. No, then we have something similar to this, and but there is some small difference. But if I remember, after eliminating some auxiliary field from this side, then we can show that they and the change of variables, we can show that they are equivalent. Or another way to prove it is that the second one is not our path, but another possibility is to introduce Stuckberg fields to restore the 4D diffeo and then compare. That is also possible. But the simpler way is to start from Cascadon and then take the unitary gauge. And then after that, we try to compare. Then the relatively easy to see the equivalent.
Is it a 3 curvature or it's a 4-dimensional one?
This is 3D curvature.
Three.
Yeah. So this part comes from Einstein part, of course.
Okay, well, basically my question was caused by the fact that recently we considered the so-called model of generalized unimodular gravity, and it's interesting that when you convert it to the form of the K-essence model, then there is a kind of a gradient expansion, so that in the lowest order of the gradient expansion you have exactly a kind of a Kuskouton model.
I see, that's interesting.
To the Einstein term. So like that. Well, okay, thank you very much.
I want to have a look at this. Yes, yeah. Very interesting relation among different theories. Thank you.
Okay, and maybe the last question, if anyone has one. Please go ahead.
It's probably it's me. Do you hear me?
Oh, yes,
Yes.
Alexander, please.
If you are working with your version of massive gravity, what about black hole like solution in your theory? Thank you.
Yes, we found the black hole solution. Maybe not here. Yes. For example, in this massive gravity case, minimal theory massive gravity, actually the any solutions of we prove that in this paper we prove that any solution of GR that can be rendered spatially flat by coordinate change is also a solution of this self-accelerating branch of MTBG, with or without matter. So in the case of spherical symmetric case, it's easy, and Schwarzschild solution is a solution, so we can represent black hole and star exterior, and also spherical symmetric GR solution with matter can be accommodated. And what is nice about this is there's no strong coupling, there are no extra singularities except for those in GR. And in the case of rotating black hole, I think there should be a modification because we know that there is no for a curved black hole does not permit allow for not only flat slicing but also conformally flat slicing. Therefore, curved black hole should be modified in this theory. But the modification should be suppressed by some ratio between the say size of black hole and the gravitational mass. So if gravitational mass is cosmological, modification may be small, but still I think it's easy, interesting to see the difference from GR. But this is not yet been done. Yes.
Thank you.
You're welcome.
Okay, thank you very much, Shinji, again.